Welcome to our podcast on pressure in fronts and how that relates to weather and the climate. If you'd like more information from your book, this is in Chapter 17, Section 2. Let's start with air pressure. Air pressure is the force of air molecules pushing on an object, which can be affected by an object's altitude and the density of the air molecules themselves. So if you've ever climbed up a mountain, you've probably felt that the air gets lighter or thinner, which is less pressure. So again, as you increase your altitude, if you go higher up in the atmosphere, the density of the air molecules is less, it spreads out, there's less pressure. The air is thinner, so to speak. And air travels from or moves from high pressure to low pressure, and that is what creates wind. Wind is the cause of air moving from high to low pressure. Barometers are instruments that meteorologists use to measure the amount of air pressure in a given area. And so to kind of review this slide, let's start at sea level. If we were at sea level, we'd have a high pressure because our altitude is low and the air molecules would be dense. But as we climb that mountain, we'd increase our altitude, the density would decrease, the air would get thinner and less pressure. And again, air moves from high to low pressure, creating wind. Now we'll discuss high and low pressure systems, starting with a high pressure. A high pressure system is a region in the atmosphere where the air pressure is higher than the air pressure around it. As a result, the air in the center of the high slowly sinks. The direction of the movement is it spins clockwise, and this is associated with clear nights because sinking air does not lead to cloud formation. So we got clear skies and dry weather associated with highs. In this picture, you can see that in a low air system, the airflow around a low is counterclockwise. As the name suggests, a low pressure system is a region in the atmosphere where the air pressure is lower than the air around it. And because air flows from high to low pressure, the air flows in towards the low pressure, and this inward flow then causes the air in the center of the low to rise. Again, the direction of this motion is counterclockwise. The next bullet talks about warm and cold fronts, which we'll be looking at in the next couple slides, so we'll save that information about warm and cold fronts for later. But the low pressure systems are correlated to stormy weather, and the reason for that is as that the air rises in the center of the system, that air rises, it expands and cools and results in cloud formation and precipitation, creating again cloudy weather, rainfall, and storm. High and low pressure systems not only have an effect on local winds, but they also have an effect on global winds, on a global wind pattern. So, and there's two factors that are producing these global wind patterns. The unequal heating due to the equator and the poles is one of the reasons, and then also our rotation of the Earth provides a factor as well. So obviously near the equator, we've got warm air, which is going to rise and create a convection current because after the warm air rises, but then cold air sinks. So we get these convection currents. And this convection current near the tropics produces trade winds. Again, that warm air rising, cold air sinking, and that's going to pull the direction of the winds to the west, from the east to the west, when we're going from 0 latitude to 30 latitude north. So their weather actually moves from east to west due to that convection current. On the other hand, we're up in the westerlies because we're at, I think, 42 degrees north latitude, and so what we're affected by is a different convection current. So again, warm air rises and cold air sinks, but the direction of this, again, due to the unequal heating of the equator to the pole and the rotation of the Earth, causes this convection current to go in a different direction, and now it affects our wind. Our wind actually moves from west to east. Hence why we call it the westerlies. Our wind is moving from west to east. Our weather is moving from west to east at that latitude. So again, these different latitudes have a different global wind pattern. These next two slides have the words that I was just describing to you. So if you want to make sure you got these written down in your notes, we will review it. So again, we can have global wind patterns due to these pressure systems. And the two you probably should jot down in your notes are the westerlies. Again, you live in the westerlies, you're in the middle latitude, so your wind is blowing from west to east. So your weather, again, if you want to know what's coming, again, typically, let's look to Nebraska. Let's see what's coming, because our wind and our weather moves usually from west to east. The trade winds, which are near the tropics, on the other hand, their wind is blowing from east to west, or their weather is moving from east to west. The reason for these differences in different latitudes, again, there's two factors causing these global patterns. That's the unequal heating between the equator and the poles, and also the rotation of Earth spinning on its axis. That's what's creating these different convection cells, these different directions in the wind patterns. Now we'll define an air mass. An air mass is a huge body of air that has a uniform moisture and temperature, or a similar temperature, humidity, and air pressure throughout. And so we've got different air masses. We could have a tropical air mass, which has warm air in the tropics and has low pressure. We can have a polar air mass, in which it's obviously cold air mass from 50 degrees north and 50 degrees south, so that's at our poles. And we can have a maritime air mass. These are air masses over oceans, and they're very humid. And then continental air mass, which obviously we're in a continental air mass, formed over land in the middle of continents, and are dry air masses. Air masses interact in zones called weather fronts, and these are also associated with low pressure systems. So weather fronts occur when air masses of different temperatures meet, and we can have a warm front and a cold front and a stationary front, and we're going to look at those three next. So here we have a picture of a warm front. Again, we've got two air masses of different temperatures meeting, and what happens in the warm front is the warm air is going to rise gently above the cold air, which is going to usually form layered stratus type clouds or fog. Again, you can see those stratus type clouds forming as the warm air rises above the cold air. And we are going to get some precipitation, typically only drizzle or a steady rain. In a cold front, the cold air is going to push the warm air up randomly and chaotically and create cumulus clouds, and it's going to produce showers and thunderstorms. So again, we're going to get precipitation, but this is going to be, again, because that warm air is pushed up more randomly and chaotically, it's going to again be more thunderstorm type activity. So the cold air again pushes underneath the warm air, pushing the warm air up, creating again cumulus clouds and showers and thunderstorms. Our third type of front is called a stationary front, and this is what happens when two air masses meet and they simply stall, so they quit moving, and the resulting boundary is called a stationary front. When these two fronts meet and stall, we get a stationary front. These are the symbols for fronts that you'll notice on maps, or perhaps as you're watching the weather forecast. They'll use blue triangles for cold fronts and a red half circle for warm fronts, and a combination of both to show a stationary front. This concludes our podcast on pressure in fronts. I hope you learned how high and low pressure systems, how their airflow is different, and I hope you learned how fronts are the interaction between different air masses and what those interaction types are. Thanks for watching.